value signals. In the frequency domains, we'll have the complex conjugated mirror at negative frequencies. So with here minus carrier frequency minus frequency of our signal, then minus carrier frequency plus frequency of our signals, and equivalently carrier frequency plus carrier frequency minus the frequency of our signal, and plus carrier frequency plus the frequency of our signal. And we already discussed last week that simply the modulation can be executed through the very same process. So we have our two signals that are arrive at the receiver, and once again we multiply them by carrier frequency, and pretty much the same principle as we discussed earlier on applies, right? So we will get the new frequencies, which will be the sum and the difference of all the possible combination of whatever we get here at the input of our mixer, right? So at the end of the day, we will have 6 different components, right? So FC, double the FC plus minus F signal, those are those two. FC minus FC, so basically the carrier frequency is cancelled, and that's pretty much what we want to achieve with the modulation, ending up with plus minus frequency of our signal. And of course, those two components, they will, well, clearly they overlap with each other, right? And then again, you know, minus double FC, still we are using here real valued signals. So we need to have always complex conjugated spectrum. So, and then of course, you know, we are interested in the low frequency filter. So we use it low pass filter, extracting our baseband signal, recovering our information, and those signals get simply filtered out, so they are kind of undesired product. So, are there any questions towards well, previous lectures, or any questions relating to this? Okay. I don't see that, but another thing actually I forget to ask the default question: can you hear me and can you see the presentation? But I'm assuming somebody would have speak out if this wasn't the case. So I'm assuming I'm audible. Okay. So anyway, from the demodulation. And this is basically the math behind it, right? So basically what we should observe now from the previous week is that, as I mentioned earlier, we have this, you know, mirror plus minus carrier frequency. So whatever is on the positive side is also mirrored by the negative side, right? And also the consequence is that we have the signal, which is carrier frequency plus and carrier frequency minus F signal, right? And the problem here is that if you look carefully, we are practically transmitting the same signal twice, right? Because F sig, you know, in both cases, it carries the very same information, right? And I know we talk quite a lot about redundancy and improving the signal. However, well, in that context, we are actually using double the amount of bandwidth that we need, right? So this is actually not always necessary. So what we can actually do is we can well, the question is here, of course, what can we do better? And hopefully, answer that should be clear is where we can simply, you know, chop off or filter one of those two frequencies, one of those two bands. All right, because one of them is clearly not needed. So why bother? We can have half of the bandwidth of our signal in this case, without practically any loss of information. Okay, and basically this is what is done with so-called single sideband modulation. So it's pretty much similar to amplitude modulation, just we use only half of the signal. And as you might imagine, the most simple approach to this is the use of bandpass filter after the modulation. The problem here is, though, that this is a very primitive approach in a way. So it works, but simply because our carrier's F signal is, much smaller compared to the carrier frequency, we would need here very accurate filtering, which, especially if you think about all the Doppler shifts that can occur, this is not necessarily the best way, although it's possible to do it this way. So you probably need high order filters with very steep filtration slopes. That's one way. That results in, of course, the down conversion becoming more complex. Well, as I mentioned, the advantage is that we use half of the bandwidth. In practical terms, how this can be done? This can be actually done by changing the alternative way is actually to embed that into the modulation process in such a way that at the output, simply one side of this one sideband of this modulation will simply cancel out each other, and that's pretty much how it is done. So this approach is used pretty much in amateur radio, especially for analogous voice. And the obvious advantage here is, as mentioned, that simply you require half the bandwidth for transmitting the same information. And as you might imagine, there are basically two types of this modulation. So the upper sideband modulation and lower sideband modulation. And well, hopefully the name tells it all. So in the case of upper sideband, we take the upper portion and filter the lower one. In the case of lower sideband, we take the lower and remove the upper one. So do you have any questions so far, or is everything clear? Okay. All right. So now another thing I wanted to consider here is so far we used, in all the equations, all the modulation we used, cosine, which basically means, we were modulating with cosine, demodulating with cosine, which basically means we assume all the signals are always coherent, they're always in phase, right? And well, basically the question would be, what would happen if instead of using cosine, we would use sine for demodulation? Does anybody has maybe any rough guesses how this would work out, or any bets?
We would get consistently wrong results.
Yes. In a way, well, it depends what you mean by wrong, but yes, obviously it won't work as well as in the previous slide.
I mean, however, I assume that we will still have correct data, but we need to be careful how we interpret them.
Well, not really. I think actually the first answer was probably more correct. So So actually, yes, you're sorry. I just needed to think a little about it. But yes, in general, you will need the wrong data. The point is, what I'm trying to show here. But okay. So yeah, because as you can imagine, right, sine and cosine are two orthogonal function, right? So basically, indeed, you will get well, wrong data. Okay, so maybe let's see how it works. So we have the cosine function. We use the sinus function for the modulation, and again, same equation applies. However, in this case, we have this case over here because we're multiplying sine over cosine, right? Like, so we still get our carrier frequency plus signal frequency component plus sinus of the negative value. However, what changes in this context is that we use sinus function and not cosinus as previously. And the consequence, so here again, same story, multiply everything. Instead of cosine, we use the sine function, and we end up with the sum of two sine functions. So, well, we have here basically our component, which is double the carrier frequency, and that's pretty much, well, it's sine, but it's still there. However, we get a sine function of a 2 pi of carrier frequency minus carrier frequency. All right. So similarly as in the case, of course, fc minus fc gives us 0, right? So we should end up in the DC. However, the problem is that this is a sine. So what is the sine function of 0? Anybody? Well, what is the value of sinus 0? It's not supposed to be a tricky question. I'm still waiting.
Can you hear me? Because I have today issues with my microphone.
Yeah, I can hear you there. Yes.
Okay, so I'm struggling. So the question was the sinus of 0, yes? So it's 0.
Yes, exactly, obviously, right? So thank you very much. So what's basically happening here is we get, sinus of the 0, which gives us 0, which basically means that all this component is cancelled, right? So we get this, at the end, we'll get our signal ST multiplied by double the carrier frequency. So we are indeed creating, harmonic components at twice the carrier frequency. However, then we multiply this with a 0, which means there are basically no DC component, right? Because obviously anything multiplied by 0 is 0, right? And this is basically so you are in a way right that what we get is wrong. And to be more precise, if we use the cosine and for modulation and sine for demodulation, we will get pretty much nothing, or at least nothing at the baseband that we are looking for, right? So, and this is one of the reasons really why we say the cosine and sine function are orthogonal to each other, because we get we simply get nothing, like zero power at DC in baseband. Is this more or less clear? to everybody why this happens.
Does it mean that we can send two streams of data at the same time? Just
yes,
face out?
Very good, very good. This is exactly what I was planning to tell in my next slide, and this is exactly what happens. So, okay, I just finished this one, right? So that's what I mentioned. And then this is exactly, okay, so I will go briefly through this slide. This is exactly what we experience with the QAM modulation. Okay, so in the QAM modulation, we use exactly the principle we showed on the previous slide, where we have two independent, it's not technically independent streams, right? Because we simply use this to encode, more symbols with the same way. But this is indeed another way of looking at the QAM modulation, right? That we have here as in phase, modulated by cosine of 2 pi carrier frequency, plus another stream signal Q. So that's our in quadrature component in the baseband, multiplied by the sinus function. And we then end up with this, which is a standard diagram for most of the quadrature amplitude modulation. So in the second slide, we're discussing QAM more or less as combining amplitude and phase. However, in practical hardware, this is much more easily executed by by using real and imaginary part, or as they are called in this context, in phase and quadrature component, right? So we here our two signals, which sorry, they will be combined, of course, into a single modulation point of the QAM constellation. But this exactly enables us to increase the amount of communication without being impacted by noise, right? That significantly. So again, we have a source of our carrier frequency. On one side, it is shifted by 90 degrees or by half of the pi, and this is basically what turns our cosine into a sine. Each of those mixers multiplies independently the signal. In one case, that baseband SI, in the other SQ, and then the two signals are merged. They go through the channel, and then the reverse operation. So you see, and the nice thing is that we simply don't just split the signal into two branches without any any filtering or whatsoever. This is done basically automatically here because, again, two mixers, if we multiply that by cosine, the sine component will vanish, and vice versa here. The cosine component will vanish here. Then we end up at the output of the mixer with two signals, one in the baseband, slowly changing information that we want to recover. The other will be, again, at double the carrier frequency. Double carrier frequency is too fast for us, so we use low pass filter, get rid of it, and we end up with two streams of real and and imaginary that on the receiver we can do then anything we need it for. Okay, so that's actually very good remark. So yeah, we basically end up with the QAM modulation from lecture 2, and that's exactly how it is done and why it works. All right. So is this clear, or any more comments, questions? All right. So yeah. So right. So with this, I will try to move a little bit more into the electronics, and basically most of the stuff here will be so-called nonlinear components, and this is something which is quite critical to the radio frequencies or RF, but in pretty much nonlinear components are basically key to any modulation schemes, right? And the reason for that is, as you saw previously, the art of modulation is very often changing the frequency of our signals. So what we're doing, we are basically creating new frequencies. So our output contains new frequency components of the spectrum, which did not existed in the input signal, right? And that's the core idea of how modulation works. And
Sorry.
yes.
Can you go back a slide?
Yep.
The question about this ideal channel. If we would have some noise in this channel, does it impact just like it's on the output? Let's say R1, it's just some distortion, or can we get like a channel crosstalk talk?
So yes, in theory, actually, again, good remark. So we could get theoretically a crosstalk if we get, for example, well, firstly due to phase delay. Secondly, if we get the carrier frequency wrong. So basically, if we got the phase delay, then of course our division into cosine and sine function will be, a little bit, well, as you call it, crosstalk. So the two signals. So here we'll meet part of sine and part of the cosine, and here we'll meet the other part of the. There'll be also different components of that signal. However, firstly, it is not significant in this context because they will be still orthogonal. So what you would observe if you think about the QAM diagrams, you will simply see that the diagram rotates by a certain angle. Okay, that's the results of the phase delay. So typically with modern radio signals, you would typically use something which is called during the handshake. There's some way basically of calibrating your system, okay, to cancel out those phase delays, right? So you basically send a previously agreed sequence of symbols, which the receiver know what they mean. It uses those symbols to correct for this phase shift, to rotate back basically the QAM diagram back to the position it was intended to be, and only then when it is so calibrated, the information can be transmitted. Okay.
So if we know the error, we can just ignore the crosstalk in the signal processing.
Yes, you can calibrate that out, right? Because even if you get the crosstalk, those two will be always orthogonal, right? So so you add what you add to one channel will be kind of subtracted from the other, right? The other possible problem that's more actually significant is basically if you get the carrier frequency wrong. Okay, if the frequencies are not well enough synchronized, and then what you would typically observe is that basically your QAM constellation rotates with time, right? Simply because frequency is the change of the phase over time, right? And if your carrier frequency is not perfectly aligned, you will observe this change. So then there are two factors that you can compensate for that. And then of course, if we don't have ideal channel, we'll have noise and all the things that we discuss on the second lecture, right? But that's something that's typically dealt with channel coding. So in post processing, right? In the coding basically of the signal. Okay. So does that answer your question?
Yes, thank you.
Thank you. Okay. So right. So again, going back to the electronics, what I wanted to stress here is that typically, by definition, nonlinear signals. If you look at the linear time invariant theory that you had during your basic electronic module, so basically, all the circuits that can be modeled using so-called RLC components, right? So passive inductors and capacitor using simple equations. Those are typically called linear components. And one of the characteristics of the linear components is that they are not able to generate output at new frequencies that were not included in the input. Right. So typically, if you get a RLC filter, it can filter out things, attenuate certain components, but only RLC circuits cannot generate new frequencies that were not from the beginning at the input signals, right? So hopefully by now you should realize that, especially with what we spoke in the previous slides, that modulation requires creation of components at new frequencies. That's why typically we need nonlinear components. Okay, so presumably either diodes or preferably transistors. You cannot do modulation, at least classical modulation, using only passive RLC components. Okay, now here we move on to this is classical radio receiver for the amplitude modulation. So it is basically called the super heterodyne receiver. So the name basically heterodynes comes from the fact that we have a external local oscillator here at the receiver. But okay, let's maybe go step by step through what's happening here, right? So last week when you talk about mixer, and I asked you about what's the way of demodulating the signal, and actually somebody mentioned using a diode to capture the envelope. And so as you see here, this is actually done indeed like this, but only in the second step. And the reason for that is it turns out actually that the super heterodyne structure is much more flexible and simply much more useful. And especially it's very practical if you have to tune to different frequency bands, right? So we all know familiar with the frequency channels. We are familiar with frequency division multiple access. So pretty much if you have a receiver, it will typically change the frequency which it wants to receive. And this is actually much more convenient, much more easy done using this this super heterodyne structure. So what's happening here is firstly we got our antenna, which accepts pretty much anything it receives, any electromagnetic waves it is able to capture, right? And of course we want to tune in to our frequency channel. So the very first step is the RF filter, and that's selective filter, basically tunable to exactly the channel we want to listen to, with bandwidth, of course, corresponding to the bandwidth of the communication of the channel, just to get rid of all the unnecessary things that can cause quite a lot of problems on the subsequent stages. So that's step number one. Well, step number two, as I mentioned earlier, the radio signals are typically very, very weak, right? They decay with the power 2 of the distance. So we have quite a lot of noise. So we want to basically amplify it. However, this is like a radio frequency amplifier. So firstly, it amplifies, directly the high frequency signal, which is not that easy. It's a rapidly changing signal. But secondly, it's very often a low noise amplifier. Okay, so the role here is that we want to amplify the signal, but adding as little noise as possible, because we are still here in the analog domain, right? And analog domain, of course, in the sense that we are operating at the carrier frequency at the non-digitalized signal, right? So we have to be really careful here with the noise. So once we got the amplified signal, we perform with the mixer our demodulation, right? So this is the principle you saw earlier on and last week, that we simply once again multiply our modulated signal with the frequency, with the carrier frequency, which is here. So that means basically we have a local so-called local oscillator. So this is typically a very stable signal generator on the receiver side, which generates the FC carrier frequency that we saw. We can multiply with the mixer, and also bear in mind that there is this dashed line here, which means our local oscillator is, of course, coupled with our RF filter. Because of course the two of them work in the tandem, right? So the center frequency of the filter has to be the same as the frequency of local oscillator. Otherwise, of course, it won't work. It doesn't make any sense, right? So here at the output of the mixer, what we got? Well, we got the baseband low changing signal and double the carrier frequency signal. So sorry, it's one actually clarification. So this is called, so then, okay, I may finish this block and then explain. So over here, we will again make a selective filter, right? Predominantly to get rid of all the higher order modulation components. And we end up with what's called IF, which stands for, we're here at step 4. We are what's called IF, which is intermediate frequency, okay? And why intermediate frequency? And why actually selective filter and not yet low pass filter? So this is exactly the whole concept of the, or the key basically of the heterodyne receiver. So it turns out it's much more practicable to have a mixer which does not really convert our signal directly into baseband, right? But it uses some intermediate frequency before it is finally demodulated to the desired baseband. And this basically allows us quite some flexibility. Also, because then it's more easy to just, tune the local oscillator to the desired frequency if it needs change. So we got our intermediate frequency. Here we once again perform amplification, and this is, even though it's not a baseband, it is already lower frequency signal. So now we can have, much more control, and then we are more flexible with adding some more amplification with our amplifier, and only then the super heterodyne architecture performs demodulation. This is the final demodulation, which is denoted here using a diode. So this is the thing somebody mentioned last week, right? That we just used the diode to capture the envelope. Of course, it doesn't have to be one diode, right? It can be that the grid bridge or whatever. And here, since we are ending up with the baseband, we have low pass filter. Then of course, once again amplifier, and here, well, it's speaker, but obviously, it can be anything anything else for which you desire this information. Okay. So are there any question towards this architecture? Okay. So one thing I should mention here, that as you see, in a way, the demodulation for the super heterodyne is basically performed in the 2 steps, and they're which dictate the output frequency, and they're all encoded here in the color, right? So the red block, this is the so-called radio frequency signal. That is, in the range of what, depending on your system, gigahertz, 900 megahertz for the mobile. Then we first lowered that using a mixer to an intermediate frequency, and well, that can actually vary, but it can be a megahertz range or somewhere around that for further amplification. And then in the second step, we already demodulate that to the baseband, which generates our sound, which well, using the example of human speech, that would be of course in the kilohertz region. Okay, and this is pretty much the quite standard, commonly used architecture for receiving the signal. Okay. Okay. So with that, I would like to move on a little bit to the more detailed solutions. And so I talk a little bit about mixers, and we all know that this is just pretty much perform the action of multiplying the two frequencies. So well, over here, this is just an example diagram of a mixer based out of two diodes, the so-called ring mixer. It's not the best one, simply because those are like passive diodes, so they don't allow any amplification, of course, of the signal. Typically with preferred transistors, but okay, that's the most simple you can get. What's kind of important is you should keep in mind that in this context, the diodes are actually put in the ring configuration, like one after another. So this is slightly different than the classical grids bridge, circuit that you might know using for the from the power supply unit. So basically what happens here, we got here the frequency F1 with, this is our RF signals, highly changing. It is coupled through a transformer, through a coil in this way, and in the middle we inject here F2, which is well, in this case, let's say this is our highly changing signal, and because of the diodes, well, basically the the magic happens. But what's exactly happening here, right? So, well, we have two different signals at two different frequencies, which are embedded together. Well, so far so good. Then we use this diode, this area of a diode here. Okay, so basically the one which is not linear anymore, and this is basically the so-called working point of the mix, right? So we really want to be around this nonlinear region in this point, and then because of this nonlinear region, we are generating some, you could call them, well, intermodulation products. Okay, which would be actually at the sum and difference of the two of our signals. So here I actually got the example of well, it uses amplifier, but the principle is the same. So typically this is the characteristic, sorry, of the amplifier, right? And well, over here we get simply linear range, which means you add X of the input power, you get Y of the output power, whereas the ratio or the slope of this curve, this is the amplification ratio, right? And well, of course, in the ideal case, we assume that the curve goes towards infinity. However, as you may imagine, this is not the case, right? So very often, well, that should be quite intuitive, right? I mean, if you just add more power at the input of your amplifier, at some point, of course, you will burn the amplifier down. But before this happens, it will kind of start operating in a nonlinear mode. So what does it mean? Well, over here you can see that if you increase the power, slowly your amplification will drop. Okay, so and it will continue dropping up to the point where you have more power at the input, but pretty much no additional power, no more power at the output. That's kind of the saturation region. Okay. Now, from the parameters or catalog data of amplifiers, you will see very often defined what is called 1 decibel compression point. Okay, which basically means this is the value of the input power for which your amplification will drop 1 decibel lower than what you would expect from the, idealized linear curve. Okay, and obviously, if you want to have a nice linear amplifier just to amplify the signal, you want the 1 decibel point to be as high as practicable, right? Because for amplification, you would simply use this range of amplifier of a transistor. However, if you want to do mixing, well, this is actually the nonlinear area is where you are quite interested. So over here, actually, this is some, this is some example of the voltage output. And maybe to see what's happening or why this compression generates harmonics or additional frequencies. I just try to use a pen. So so basically let's assume this is your input signal, right? This is the sine. Okay, this is the sine function that you're working with. And basically, let's assume that you are, working close to this point. So over here, once your sine increases, you are still within the linear range of your amplifier, right? However, if so, let's say this point here, the amplitude increases, so that your input power will get you up to this point. And the consequence of that is simply that the peak of your sine function will be compressed. I hope that's quite clear what I'm drawing here. Okay, so basically it begins as a perfect sine function. However, the peak of the sine is not really chopped off, but it's compressed. So technically, this is not anymore a sine function. However, it's clearly still a periodic function, right? Because, well, obviously, you will experience, the same compression for the same input power, right? So you end up with a strange periodic function. And hopefully, as you might remember from the lecture, well, a few weeks back, any periodic function can be actually described as a superposition of harmonics, right? So if you got a pure sine function, it will be just a single peak, well, plus possibly DC if it's moved up or down. But any other non-sinusoidal harmonic function will be seen as a sum of harmonic at frequency f, 2f, 3f, 4f, 5f, and so on, right? So basically, therefore, by using sine function at the input with the compression point, by compressing the peaks of the function, you end up with non-sinusoidal harmonic function, which after doing the Fourier transform will be seen as as having additional frequency components. So far, is this clear? Or do you have any question towards that? Okay, so of course, as you can see here, what exactly harmonics will be with, what amplitude and so on, that will depend on the shape and on the, how much compression is executed. However, you basically generate new frequencies where there were not. Okay, so and yeah, this is more or less how it will work. So apologize for the Polish subtitles here. So this is the again here. This is the characteristic of your amplifier. So this is input power, output power. The black curve here, this is the linear range, where it really just amplifies the signal that we are interested. Over here, this is the nonlinear range. And we can see that the red curve, this is, well, this is basically the input signal, or basically actually signal that is, yeah, the input signal. And then the output for the nonlinear range is, of course, we get amplification. So the output peak here is much stronger. However, we've generated the first harmonic on double the frequency, second harmonic on triple the frequency, and so on and so forth. So that's basically how it works. All right. And then, of course, if you add two different signals, well, the same will you will experience exactly the same thing. However, you're not anymore limited to generating single harmonics, but you will have intermodulation products. Okay, so basically, what will happen that you will see your signal multiplied not only by integer multiplication of a single component, but also by what's called by the combinations of sum and difference of the two signals. And this is actually what we use in the mixer to get this modulation, to get the multiplication of the two signals. However, you have to be careful here, because it may also occur in your electronics where you don't want it to be. Okay, so let us assume we are having our antenna, and as I mentioned, antenna accepts pretty much most of all of the signals that are over there in the propagate through a free space. Okay, and there's no selection, so it may happen that we have accepted two signals at two different frequencies. So what happens here? Well, we will basically, when we reach an amplifier, and the amplifier is operating in the nonlinear range, well, we basically get the same thing as with the mixer. So although in this case, of course, we don't want this mixer, because we don't want to, so it's an undesired process in that context. Okay, so, but we have here the dual frequency signal, which is input amplitude 1 multiplied by sine of omega 1 plus amplitude 2, at the frequency omega 2. And then because of the nonlinearity, so here it's formally described that the V out is K1 at the V in plus K2 times V to the power 2, and so on and so forth. So this is basically describes mathematically what's happening here. There's this compression in the amplifier. Okay, and if we move through the output, so okay, the K1, this is our linear component. So that's straightforward, just amplification. We get K1 multiplied by one signal at one frequency plus K1 amplified by amplitude 2 at the second frequency. That's fine. That's more or less what we want to get. However, bear in mind that the second term, it uses square root of the input signal, and only this is multiplied by K2. So we have, A1 sine omega 1 plus sine 2 to the square. And as you can see here, we need to, from the, equations on power 2 of the added numbers, you should instantly see that this will end up in this square root, power 2 of this function. So that will be responsible for our second or first order actually harmonics, or sinus square 2 omega 2 plus sinus omega 1 times omega 2 plus sinus omega 2 to the power 2, right? So basically, we will see the purple signal to the power 2 plus multiplication of those two signals plus the red signals to the power 2. Okay, and then of course, if I mention of multiplication of the two signals, well, then that should let you some red flashing light in your head, because this is exactly what we talked earlier. What happens with the mixer, right? So you're generating additional frequencies. Those are called intermodulation products. Okay, and then of course, well, I mentioned that the power 2 or second order component, but of course we can see here there are like third, fourth, fifth, and so on. Typically, of course, the K value will typically decrease, so the higher order components will be less problematic because they will be more attenuated. However, they may also exist, and this leads us to the intermodulation products. Okay, so if we have two different signals, here is F1, F2, that's the two signals that we want to receive. And then because part of that signal might get mixed up due to pretty much any nonlinearities in our either receiver or transmitter, or in some cases even within the channel, the process can occur. So we get undesired new signals at double. Well, okay, so this is the harmonics. That's double the F2 simply, and then over here, actually maybe change the color. Okay, so let's say blue. This will be our first order harmonics, so F1 plus F2. Okay, and that's okay. Well, there will be, of course, another one at the negative frequencies, as we know earlier. Okay, so we got the first order or the second order harmonic, F1 plus F2. Well, it is not nice because you can imagine that there is, they might be your neighbor or some other signal that you get disrupted. So it is a problem, but if you think about it, it's not necessarily a big problem. And the reason being that this frequency here is very far apart from your two carrier frequencies. So if let's say you're designing a receiver a transmitter, you realize somebody or you did a mistake and a bad job by having some nonlinear components while you're generating intermodulation products. This can be pretty much filtered out simply because it's double the sum of the two frequencies, so it's nicely separated with from the useful signals that you have here. So basically, as long as you realize there's a problem, you can correct that with a filter. That's not an issue. However, as I mentioned, the problem will be with the third order harmonics. Why? Well, because with the third order harmonics, you get double one of the frequencies minus once the other frequency. So you can see here, I will mark this maybe with, I don't know, let's make it orange. Okay, so this and these two peaks, those are basically the third intermodulation products. And you can see here that typically they are located very close to your useful signal, right? And to be precise, they will be located the frequency separation, which is exactly the difference between the two signals that gets into the intermodulation. Okay, so typically from that point of view, third, fifth, seventh, and so on order intermodulation products can be actually much more dangerous, simply because they are located much closer to your useful signal that you want to do something with. So it's more difficult to filter them, and you might be interfering with yourself, right? Because here, of course, we got quite narrow band, nice peaks, but especially if you have more wideband signals, this can be a significant problem. So, for example, if you think about LTE systems, the 5G, they tend to use actually quite a lot of different frequencies, simply because, as we know from previous lectures, the more increased bandwidth allows you to transmit more information, right? And this is what we need when we do streaming video to our phone, or that's a lot of data. So we need bandwidth for that. Also adding all the users. However, because the bandwidth, as I mentioned, is quite heavily used, it was challenging to have like a single block of bandwidth from the beginning, right? So some of the frequencies are kind of scattered across the spectrum. And that means that LTE is using quite a lot of different frequency bands, quite a lot of different carrier frequencies, which again means it is very prone for intermodulation. Okay, simply because the more frequencies. So here actually we discussed only two input signals, and you can see there are already quite a few peaks that are being generated. Right now, if you add, let's say, 5 different signals, now each of them firstly will generate harmonics at integer multiplication of themselves. Secondly, every combination of those 5 out of those 2 signals will generate, second order harmonics at the sum and the difference, then third order harmonics that you see here. And this will be happening with every of those 5 signals. So at the end of the day, with greater number of frequency, greater number of signals, you will, if you don't do, of course, anything with that, you will have quite a messy spectrum with quite a lot of undesired contributions. Okay, and is this clear? Any questions so far? Okay, so yeah, again, this is something that has to be kind of taken account and engineered. In practical terms, when you do the simulation or testing, you would very often use so-called dual frequency excitation. Okay, because of course, if you got the classical analysis with just a single frequency, you won't be able to see that, right? So you basically need to. So when you're looking basically for intermodulation products in your system, you always need to use a dual tone excitation, and then look what is the signal level at all the combinations of interest, right? So the sum and difference of the two frequencies, double, and most importantly, the third intermodulation product. So double one frequency minus the other one. So that's how you have to test and check whether you don't generate any undesired bandwidth. And well, as you can imagine, hopefully this is not always an easy task. So it takes quite some experience, simply because, well, it's nonlinear. So it's very easy to miss something simply because, your test involved not enough power to drive the nonlinear range, or there might be some, it's simply easier to miss things, simply because the tests are complicated and they're non-linear. Okay, so basically then we have fifth order intermodulation distortion or intermodulation products, and well, to generalize, any order intermodulation distortion comes from the fact that of this thing here. So basically, if we assume the new frequencies will be generated as k times f1, so one frequency, plus m second signal, and k and m will be integers, whereas the sum of those will define which intermodulation product we will have. Okay. So in the case of third order intermodulation, we would have, once f1 plus minus, actually, because it should be plus minus here, m2, so 1 plus 2 is 3, right? And those will be all the combinations. Now, then if you move to the fifth order intermodulation products, any combination here of k and m, which give us number 5, will be a fifth order intermodulation product. So as you can see here, we get to generate quite a lot of new frequency, because there are 4 possible combinations of k and m, which gives us 5. We can have, k equals 1, m equals 4, k equals 2, m equals 3, k equals 3, m equals 2, and then k equals 4, m equals 1. Okay, and then each of the combinations will come with plus and minus signs on both sides. Okay, so here we are kind of assuming that we have 2 signals, one at 3 gigahertz, the other at 4 gigahertz. Okay, so let's try to follow up this. So we get one frequency, so 3 gigahertz plus 4 gigahertz, we generate 19 gigahertz signal. That's quite high frequency components, but okay, this one is relatively away from this. And then we also generate for -1 and +4 the 13 gigahertz component, which is, again, we're generating another high signal frequency. So it won't directly impact our system, which works between 3 and 4 gigs. So we can say it is someone else's problem. But of course, if the regulator or that somebody comes to you, well, in a way, you might be also in a problem. Then, of course, we got the negative frequencies, which, as you see, mirror the positive ones. So it just comes from swapping the plus and minus signs. And then similarly for the 2 and 3. So we got 18 and 6 gigahertz signals. Well, the 6 gigahertz would be probably out of the fifth order IMD the most problematic one, simply because it's close to our original signal. So it's in that case, because it's a fifth order, it's double the difference between 2 signals. So 6 gigahertz away from what we have here. And then similarly on the other side, we get like 1 gigahertz over here, right? So those closest will be probably the most problematic. the point here is that at the end, with the first order intermodulation products, using just two different frequencies, we generate quite a lot of new signals, new frequencies. So we get extra signal at 1, 6, 13, 1, 6, 13, 16, 17, 18, and 19. Is that? Yeah. So we got pretty much eight new components, which might interfere not only with our own system, but also with somebody else's system. So this is the way how we can potentially generate quite a lot of harm, especially for wireless systems, wireless communication signals. So that's something that you should be aware with. And the question is how to deal with that. So in principle, when you look into many of the amplifiers here, so here we're actually discussing the situation when we are not doing any intentional modulation. We are just trying to amplify signal, and then the intermodulation can spoil the performance. So there is a figure of merit, two key figure of merit. So there's this 1 dB compression point, which we discussed earlier on. So this is basically the point for which you apply certain input frequency, and your amplification drops 1 dB below the expected. And if you reach that point, that means you will start seeing some significant non-linearities. Right. So typically you shouldn't, if you're buying an amplifier and you see in the data point that you have a certain value, it's typically between 10 up to 20 dB of sorry, no, that's nothing. So basically, if you operate with the 1 dB compression point, this is more or less the limitation of the power you can input to your system, okay? Because if you operate too close, or especially above the 1 decibel compression point, well, then you might experience some non-linearities. Okay. The other figure of merit is so-called IP3 intercept point. So this basically IP3 stands for intermodulation product free. So as I mentioned, all this is usually the most problematic, simply because it will be the closest one to the two signals that you are generating or you are using. So what does it mean? Well, basically, once your non-linearity starts somewhere here, and of course, initially the IP3, it will start, kind of gradually, right? So of course, at the beginning you will see some additional components, but they won't be yet very strong. However, if you keep increasing the power, you move farther and farther into the nonlinear range. At some point, your intermodulation products will have pretty much the same amplitude as the amplitude theoretically expected from the just linear amplification of your amplifier. And that's basically your IP3 intercept point. Okay, so contrary to 1 decibel compression point, IP3, it's a figure of merit, but it doesn't mean that if you are below this point, you are safe. So I mean, in the sense, in the case of 1 decibel compression point, you know that if you apply power below that point, it directly means you should generally not have problems with nonlinear behavior. So we're talking here both harmonics and intermodulation. Whereas for intercept points, well, if you reach intercept points, that actually means you have same power for intermodulation products and as you would have for your amplification. And actually your amplification is compressed, so it will be much lower. So that basically means you're really in huge problem even before reaching IP3. So the IP3 is like a useful for modeling behavior, But of course, it doesn't mean that you can operate up to IP3 intercept point. That's not the idea here. Okay, so are there any questions again, or anything unclear, or anything you would like to clarify? Okay, I mean, I know generally speaking, the nonlinear components are much less intuitive, and this is something actually much more difficult or challenging than which might be used from the standard LTE, so linear time invariant systems that you typically do on year one of your studies. However, as you see, especially with telecommunication and modulation, you really cannot get around it, because you cannot do modulation with only linear component. Okay, simply because of the fact that the math or the core idea of modulation is creating new frequencies which were not present in your input. Okay, is this, again, any questions, comments? All right. Okay, so that's for the moment concludes our part on the modulation and on the electronics. Okay, and briefly, we have 15 more minutes. So I wanted actually to move on to more high-level topic, and the topic of cell network or mobile communication. So I guess you're all familiar with well, you have some smartphones, use mobile communication, so this should be quite intuitive how it works from the user point of view or user side. You might of course also hear the terms like 1G, 2G, 3G, 4G, up to recent 5G, right? Which basically denotes the the generations of the technology. So basically, first mobile phones actually came up back in 1979 or previously in the 80s. And this was basically nothing like what we know so far. So those were basically analog only voice devices, quite large and huge. You can see some of those here. Well, the technology was of course much immature then, but most importantly, with your mobile, you could do only voice. So, and they were firstly operating with analog signals, right? So the quality was not very great, but well, back then it was something, right? That you could have a phone which you carry anywhere you want. Okay, so then in around 1991, we got what's called the 2G communication. And this is basically when the communication was moved from analog to digital. Plus, there was a possibility for transmitting some very simple data. So by very simple data, I mean text messages. That's where they originated. As far as I know, originally what's happened that the 2G standard was allocated certain bandwidth or channel, which was dedicated for maintenance of the network. So, basically a base station reporting technical issues or status to the network. And apparently somebody realized that when the first deployment came, not all of this is really required, so that they know the technical, the maintenance data are much less than they were supposed to be. And as usual, somebody thought, okay, we can actually make money out of that. So they use part of that technical channel for texting or for short messages, and that's where they originated. And then we go through the evolution through third generation, so 3G, where additional services were added, also positioning based on triangulation with or signal strength from neighboring mobile base station. And now we have kind of 4G, which is, well, it's got pretty much internet integrated into that, much more data throughput, of course. And now slowly but surely we are moving towards the 5G, five generations. So basically this generation, it's just it's a bit of branding in a way, but it's a standard which tells us, what is expected from the system, or how much connectivity we can have. So there's just some formal definition. So we're talking about mobile communication system. So that's a system which allows a communication between mobile devices. They are called like terminals. So for example, your phone in that regard is a terminal. They are done within a given area, use radio or wireless signal, and they use what's called base stations, right? So you have a base station which collects radio signals from a certain area called cell. Hence the term cell communication, or well, popular in US term cell phone, which technically is not necessarily accurate. And then the base station then processes this information and make the connectivity. So here again we can see this is the distinction between core network and access network. So this is something we spoke a bit in relation after the optical fibers. Okay, so basically here we got a phone or terminals, and it doesn't of course have to be a phone. It is communicating with a base station. There is a base station controller, and this part, this is actually access network. Radio, because it's communicating over radio. So this is a typical access network with multiple branches, with some communication throughput that is high, but moderately high, I would call it. Then the information is transmitted to the gateway, and then it enters what's called the core network. So as you know, the core network is basically a network with connection between large hubs. That's with very long distance, very often with very high throughput, right? So basically this is when where your call is routed between different cells. It can be routed, of course, to the phone network. It can be routed to the broader internet. Most likely it will be directed to another radio access network, and then also to somebody else's phone. Okay, so this is the division between, again, access network, which as the name suggests, that provides access to individual devices, individual user, whereas the core network is the backbone of the system, which makes the most of the connection and behind. Okay, so we mentioned that we have a certain area that is divided into multiple cells. Typically, each cell is served by a single base station to provide the radio links towards terminal devices. And typically it's described as a public network with dominating private connections. So what that means? Well, basically public means anybody who can afford can use that network. You just go to whatever provider you like, sign a contract. There's no and you can use the network. And in this context, private connections, simply mean that you can, when you make a call, you make a dedicated call to one person, and this is considered private, like private from the point of view that it's not easy for unintended user to listen. I mean, of course, if you go to the security agencies, police, NSA, whatever, they have dedicated equipment to filter out and decrypt information. That's a bit different story. However, of course, as a rule, the connections are private in the sense that you cannot or you shouldn't be able to accidentally eavesdrop somebody without intention to do so. That's probably the best definition. And by the way, private and secure, those are two different terms and they should not be confused. Okay, what is important, of course, we are building a network, which means the coverage is much larger than the coverage of a single cell. Well, again, that's hopefully quite intuitive. And also each operator of the network is assigned limited resources. So in this context, limited resources means bandwidth. So typically what's happened is that when the new frequencies become available to be used for the mobile networks, well, the government will make an auction or a bidding, well, simply selling the right to use certain bandwidths to whoever gives the highest price typically. And especially with 3G and 4G, it was actually quite a significant income for the government. Right, so basically, the right to use bandwidth costs quite a lot of money, the mobile operators, and of course they get it back in the charges you pay for your phone. Okay. Also, very often you have some specialized services to, well, basically to keep the network operated. And the last point, which I would like to focus a little bit, it allows for the frequency reuse. So what does it mean? Well, we already saw this slide earlier on with the radio communication, and back then, of course, the conclusion was that it's much more efficient generally to have multiple small transmitters covering certain regions than having one big. And this is exactly the idea of the cellular system or the cell network. So we indeed divide the area we want to cover with the phone to cells, build one radio transceiver base station for each, and then put them into a network to use the synergy effect basically. Now we already mentioned, and one of the good things is that we can use the same frequency throughout the network, right? So basically, the two different base stations can operate at the same frequency assigned to given provider. However, we need to do it in a kind of a smart way, simply because we also mentioned that if the two neighboring cells are using the same frequency, they will experience interference, okay? And at the end of the day, this causes problems. So we need to make sure that we plan the frequency reuse or the using of the same frequency in a smart way. Okay, so overall, however, this allows us to, as I mentioned, significantly increase traffic capacity. And I think, well, before we go further on, I think I can stop the lecture for today here. So again, are there any questions or any comments or anything you'd like to ask?
Can I ask you something to the super heterodyne receivers?
Of course, yes.
Yeah, so if we have like double conversion on multi-conversion super heterodyne receivers, what's the advantages of going down the intermediate frequency? Like, is there any advantage of having low intermediate frequency, or is it?
That's actually that's a good question. So basically, here, so just going back. Actually, good question. So typically, I believe generally it would be more okay. It depends, of course, on the specific context, right? But generally speaking, you should have, well, the lower you go with the frequency, it's much more easy to design, electronical devices, or to be precise, low cost electronic devices. Yeah, but again, I believe this will depend really on the exact frequencies and the use case, right? But I would say rather, I believe I would go rather to the lower side. But again, it's really more about the hardware that you're able to use, and also cost of that hardware, simply because the high frequency hard components are much more expensive, right? So that's something, well, more expensive and less kind of efficient in terms of performance sometimes as well. So that's maybe a bit. Does that answer your question, or?
Yeah, I mean, I know what you mean, but I've heard that like the very old receivers for the AM and shortwave, I've heard that they had the problem, like even before the war, that very low IF introduced whistle, like the whistling noise, at like short waves. So if the intermediate frequency was around 200 kilohertz, let's say, it was better for the long wave to reject the mirror images. But for the higher frequencies, you had the mirrors so close that you could listen to them sometimes.
Yeah, that actually would make sense, right? Because this got, I believe, all to do with the intermod. Well, I think that's got to do with the intermodulation products that you are
yeah, inside
right?
the radio itself, yes.
Exactly right. So basically, yeah, that's why they wanted to give the direct answer, because it really depends on the ratio. So the rule is, as I mentioned, that if you're using any two signals, right, the difference between them, this is and the multiplication of that would generate the all intermodulation products. But as I mentioned, the third one would be the most the closest one, right? I also believe, this is a little bit speculative on my side, but I think back then the problem might be, also that the filtering was, not so great, as well as the tools for analysis were so great. So, nowadays really get dedicated methodology and dedicated simulations, right? Which, using this dual tone excitations, allows us, to calculate what is, permissible power, right? And then counteract on that. Whereas with the old transmitter and receiver, there were back then no computers with CAD simulation tools that could, simply calculate the accepted level of power and intermodulation. So I think some of those problems might be simply coming from the heritage of the old devices.
Yeah, I guess that's possible. And also, like, is there any, because the next conversion can give us better filtering of the intermediate frequency, but they also will introduce the noise. So can the previous stages intermodulate with the next stages of intermediate frequency?
I'm not, so basically you are referring to the case when you have two intermediate frequencies, right?
Yeah, and the one is going lower and the second is also going lower.
Yes, so in theory, yes. I mean, basically, I mean, the rule is simple, right? If you got any multi-tone excitation, you add it to the nonlinear component here, right?
Mm-hmm.
You will also get the intermodulation components. In theory, this is exactly the role why we have, filters at every stage, right? So
yeah.
In perfect world, you shouldn't have that problem because the filters should, filter perfectly all of the undesired frequencies, right? Assuming, of course, they're well tuned, assuming the filtration is very good, they are high order, and so on, right? So, of course, in practical, there is quite a few things that can go wrong in the process, right? So it's very often an issue of the individual components, really, right? So I don't think there are much general rules here, right? Other than, okay, so for amplifiers, the general rule is you want it to stay amplifier, so not to drive it, anywhere through close to the nonlinear range. So here comes the 1 decibel compression point, right? And typically, of course, when you see for many devices, so-called dynamic range, right, will be defined between the noise floor, so the minimum noise, and the beginning of the nonlinear range. Those are typically the two limited factors. So of course, noise limits the minimum power you can distinguish, and nonlinearity typically would limit your maximum power. And everything you got between this is what's called dynamic range of your device, right? So RF amplifiers, you don't want to drive them into the nonlinearities. So this can be engineered. With the mixer, this is where you have to be careful because that you actually need those nonlinearities, right, to generate your signal. But then you should design your filters carefully, right, to see you led to the next stage only what's useful, what's needed, right, and filter out all the intermodulations, which again, in the case of third intermodulation, might be challenging sometimes, might require narrow pass filter. Okay.
Yeah. Okay. Thank you.
Thank you. Okay. Any more questions? Okay. So with that, actually, I'd like to thank you for nice comments and discussion. So that's really well, it's always nice to hear you got some good ideas, and thank you for this. And with that, well, I'd like to wish you, as usual, a very nice weekend, and take care, and see you next week. Goodbye. Thank you.
Thank you. Bye.
Goodbye.
Thank you. Bye.